Hello, good day. Welcome to today's lesson. Today's lesson we will be completing part 2 of the unit Spatial Data Input and Collection. This week we will be focusing heavily on areas of remote sensing, that would be aerial photos and satellite imagery. So let's start with aerial photos and some basics about photo interpretation. So the aerial photos and the satellite imagery, they are among the most important and widely used data sets, and they're commonly utilized kinds of remotely sensed data that is used in land resources. For example, you're managing forests, agricultural lands, etc. It's used for cartography, that is map making, and appraisal survey in both public and private sector. So appraisal, for example, in terms of land assessment, property boundaries, determining property boundaries, etc. They are often considered part of the base map. And for those of you who may recall, I think we talked about this in class briefly. The base map is a map that shows certain fundamental information that is used as a base upon which you add additional data of a specialized type over that base map. So typically the base map will contain information that can be utilized in a number of different contexts. So how do we use aerial photos in GIS? We can use aerial photos for surveying, that's land surveying, as well as topographic mapping, that is the mapping of the landscape. So the aerial photos can facilitate the measurement and identification of both your horizontal and vertical measurements, for example, distances and location, as well as heights of the objects on the land. Aerial photos may be used for that. Aerial photos may also be used to actually identify categories of spatial features on the Earth's surface, as well as assign labels or characteristics. In other words, the attributes, assign attributes to them. For example, it may help to determine feature characteristics in the land use mapping type, such as the various vegetation types, soil type, lakes and water boundaries, geological formations. So aerial photos, and this would not just be your basic gray photo. A lot of technical manipulation will have to go into the aerial photo to facilitate some of the higher levels of data extraction. Data extraction meaning the identification of features on the land surface. Now, aerial photos may come in two forms. The most common type would be your black and white, or it may be available as infrared photos. Note that the two different categories of photos come within two different wavelengths. Black and white photos come within a smaller wavelength, whereas infrared photos come within a larger wavelength. Those wavelengths ranges have been defined there for you in terms of micrometers. Okay, it's important to note though that a lot of aerial photos, when they come to you, they can come with distortion. Alright, so the images may be distorted. Some of the reasons for that may be the lenses that took the photo of the landscape may not have been exactly vertical. It may have captured the images at an angle, because remember, these images, these aerial photos, would have been captured by equipment and sensors that would have been mounted on aircraft that flies overhead. So if it takes it at an angle, you're going to get some distortion in the image. Additionally, distortion may result if the terrain is complex, such as hilly terrain, because you typically don't normally find completely flat landscape surfaces. So as a result um, of these imperfections or these errors in the images, those would be the raw images, a certain amount of processing of the images need to take place. And one of the first things that you would have to do is you will have to georeference the image. So before entering the photo information into any GIS database, it must be transferred to a ground coordinate system for computation of distances and areas. So please be reminded, when you have an image, before you can use that image in GIS, it must be georeferenced. Without georeferencing, remember that image has no geographic context. You cannot actually identify a location, so it must be georeferenced. So the process of adding geography to the image is called georeferencing or georeference. Now, if you recall on the previous slide, we talked about the fact that the images themselves, the raw images, will have distortions. Alright? Those distortions have to be removed. So the aerial photos that contain distortions, they don't maintain a constant scale across the image. So that means, for example, features will be distorted. They may be distorted in terms of size, in terms of angle, shape, etc. Those distortions, need to be corrected. So the process that, or rather the end product of having corrected those distortions, that end product is called an orthophoto. So the orthophotos are corrected to remove relief distortions caused by the camera and the terrain. As mentioned before, the images are normally in black and white. Alright. Digital orthophotos, so that is really what the end product would be. It would be in a digital format. They are corrected to have constant scale, so those distortions have been removed. And that means that in this state, this corrected state, it is now possible for you to extract accurate measurements of features such as distances, direction, and areas of features from that image. And this is the type of aerial photo that you would want to include in your GIS and orthophoto. Alright, let's talk a bit about remote sensing in general. So remote sensing, we would have talked about this before as well. So remote sensing, we know, is the process of collecting information about the Earth's surface and the features on the Earth's surface without being in physical contact with it. Now this was a process of data collection that was used as far back as the 1960s. It was most commonly used by the US and Russian military for the purpose of reconnaissance work over enemy territory, the collection of information. Eventually, it became increasingly used in government circles as well as research institutions, and now it is available from private contractors and private providers, for example, in the form of satellite imagery. So remote sensing products such as aerial photos and satellite imagery is now more readily available to the public, though it would, in some cases, it would be very expensive if you're talking about satellite imagery. Alright, so the remote sensing technology has two basic operation modes. So basically what I want you to know here is that you have two categories. You have the visible type of remote sensing data collection. This is what relates to the reflected sunlight. So the reflected sunlight is usually what is visible to us, and also what is re-emitted through thermal radiation. So for example, like when concrete surfaces get heated up and it's releasing that heat. If you look carefully, you can actually see how the air bends with that heat being released. All right, so this is one category. It's a visible category, and then we have a non-visible category. All right, where the energy is transmitted via microwave portions of the radio frequency spectrum or the electromagnetic spectrum. So there are two categories in that spectrum: what is visible and what is not. So what I want you to really pay attention to is this little note here. What type of energy is provided, energy signatures is provided in aerial photos? It captures visible energy, so only what is reflected off the Earth's surface or any other surface. Satellite imagery, on the other hand, can actually capture visible as well as non-visible energy. So it can capture a broader range of spectrum of energy transmission from the Earth's surface. Okay, so that is satellite imagery. So in other words, satellite imagery is a little more versatile because it captures a broader range of energy signatures. Additionally, remote sensing data. So remember, in our case, the remote sensing data we are most interested in would be aerial photos and satellite imagery. So this data, after it has been geometrically corrected using georeferencing, it can then be overlaid with other GIS data in raster form. Alright, so the aerial photos and the satellite imagery would be represented in the raster data format. This is for those of you who may not be familiar with it, this is the electromagnetic spectrum represented here for us. And here is an example of the wavelengths that we were talking about. Okay, so note this portion here, actually this red circle portion is what we were really looking at most: visible, infrared, and microwave. Alright, and these, if you see here, these are a variety of wavelengths, visible being a little bit shorter, and as we move towards microwave, it becomes a little longer. Alright, so as it becomes longer, it becomes more and more difficult for the human eye to see. Alright, whereas on the flip side, the shorter it gets, it is also difficult for the human eye to see. So for the human eye to see, it must fall within a specific range of wavelengths. So moving on, here is an example of satellite imagery. So this is maximum likelihood Morro Bay 7 bands. So the 7 bands actually represent the number of bands or wavelengths that have been captured by this image. Those different various bands and categories within bands have been represented using different colors. They actually have assigned attribute information to the different colors, but the different colors actually represent numbers representing the bands or the wavelengths. Alright, so this information here is an example of land cover or vegetation maps. It enables analysis for environmental monitoring and mapping change. So if you look at the cover here, you see vegetation, you see seawater blue, so this looks like a coastal area. Alright, so we get an idea of what the land cover looks like. But this is a satellite representation. Notice it does not look like a photo, but satellite images can be manipulated to look like a photo image. This is another example of a satellite image here. Again, this is coastal, and this is an example of an infrared portion of the electromagnetic spectrum. Here we have a little description as to what we're seeing going on here. Lighter areas are where energy is reflected. The red areas are areas where energy is absorbed into the surface and re-emitted. Typically you would find those red areas would be more natural areas. Those areas where you find greater reflection taking place tend to be more urbanized areas where you have concrete surfaces. All right. So what are some of the advantages of using remotely sensed data? Remotely sensed data can cover large areas, whether you are talking about aerial photos or satellite imagery. They can cover large areas as compared to if you have to go out into the field and collect data. Of course, the satellite images would capture larger geographic areas than the aerial photos because you have the data is being captured out in the Earth's orbit, which is further away, and therefore they can capture a larger geographic extent. For satellite images or satellite data capture, they can capture extended spectral range. The same thing we were talking about before, that it can capture both visible and non-visible energy signatures. So detection of wavelengths outside the range of human eyesight allows us to detect features that would not otherwise be visible. For example, it can capture differences in the health of vegetation. For example, sick vegetation will give off a different energy signature from healthy vegetation. It can capture survivors under rubble from an earthquake. For example, living human beings will produce energy that can't be captured. If you have dead bodies under the rubble, they would be as well as living persons, the rescuers would be able to prioritize their search and rescue. Satellite imagery also gives you geometric accuracy, meaning remotely sensed data, especially satellite data, can be easily converted to geometrically accurate spatial data, meaning it will have correct shape, size of features and location of features. So it's actually easy. When you capture information with satellite imagery, it automatically gives you geometrically correct data. With aerial photos, you have some work to do first. Remember, you have to georeference as well as remove distortions to get orthophotos. Alright, so this is just a reminder for you. So when you look at the PDF of the same document, you'd be able to review this reminder note. Additionally, I just want to point out here that remotely sensed data, and particularly satellite imagery, it can be a permanent historical record. When you capture an image, it's like a photo. The images are fixed in time, thus the condition at the time of the image was collected can be analyzed many years later. If you have a series of them, you can actually perform change monitoring or temporal analysis, as we may call it. Temporal coming from the word time. Okay, here is an example of one of those for change monitoring. So we have two images here. This one is of the same, each of the same landscape, one from 1984, one from 1991. And if you look carefully, you can see some differences in the landscape. So the pink areas represent deforested areas. Dark green is forested, and the light green is replanted on new growth. Alright, so if you compare the two, you can see the most obvious thing to see here is that this 1991 photo, you can clearly see there's an increased area coverage of deforested areas, but you also see variations between the light green and the dark green. So an example of this type of temporal analysis or change monitoring, this can be used by planners to recognize areas and issues of concern so that they can make plans accordingly. So what problems can arise in terms of inputting and editing remotely sensed data? So there are two main problems that we will identify here. The first one involves problems that can come out of the manual operations. When you collect the data has to be manipulated and cleaned up. Any kind of GIS data you get, remember, you always have that stage of editing in order to clean up errors. And when we collect images, whether it is aerial photos or even satellite imagery, we can get a type of error called noise. And what is noise? Noise would be where parts of the image where you would have scattered pixels whose form do not conform to their neighbor. In other words, a little fuzzy area in the image that just doesn't make a whole lot of sense. Alright? And a large amount of manual work is often required in order to fix that, which can result in a lot of time and money being spent. So what can be some reasons for this noise that may show up in images? There may have been a problem with the sensor accuracy. Maybe there was some fault or some malfunction with the sensors on the equipment. Another very common one would be atmospheric attenuation and scattering of energy. What does that mean? There is meaning that there is something in the atmosphere that prevented the image from clearly being captured. Sometimes it could be something as simple as cloud cover in the atmosphere. Sometimes it can be dust. It can be moisture in the clouds. So any of these things can actually prevent the clear capture of images. So this would be considered noise. Additionally, shadow effects on the Earth's surface. So if you have shadows on the Earth's surface that may be cast as a result of maybe the hills and the angles of the hills, the angle of the sun being reflected on the Earth's surface, etc. All of these things can actually pose difficulty in terms of capturing the information that you need, and those interruptions we call noise. Another problem could be the unreliability of input data. As input involves many kinds of errors, mistakes and misregistration can happen during that manual input process. So remember, once we have to do any kind of data correction, it now involves human intervention, and that human intervention can actually cause some errors. Okay, for example, we talked in previous classes about keyboarding errors, misunderstanding equipment, misregistration, meaning errors in the, for example, errors in the georeferencing process. All of these things can happen, and this can seriously affect the quality of the data and therefore the reliability of the data that you use in your GIS. So this is a very important stage, your data correction stage, that a lot of time and effort and money must be put into if you want to have good quality data in your GIS. So what do we need to consider when we want to decide whether aerial photos or satellite images are most appropriate for our GIS. One of the things you would want to consider is what is the intended use for the intended use, that is, sorry, what you need the data for will actually determine the level of spatial resolution. Okay, so if your particular need requires a whole lot of detail, it means you want high resolution. And if you want high resolution, you may want to go for satellite imagery, because satellite imagery now provides very high levels of resolution. So I have a couple examples here for you all over the years from 2001 to 2014, where we can clearly see that the level of resolution has been increasing. Remember, this when it comes to satellite imagery and raster data, the smaller the pixel size resolution, the higher the resolution. So notice from 2001, it was for this is the satellite name and launch. QuickBird was the satellite name and it was launched in 2001. The resolution was at 2.44, and then by 2014, with the WorldView 3 satellite launch, it was now down to sub-meter, 0.31. So that's sub-meter. Now they are down to mere centimeters. Okay, so photographs used to historically have greater resolution than satellite systems, and maybe as fine as a few centimeters. However, developments in satellite technology has now outpaced that, and they now have a more competitive advantage in terms of levels of accuracy. Okay, so however, if generalization is acceptable for you, you don't need such high accuracies, you can go with aerial photos, because at the end of the day, the aerial photos are actually more affordable than the satellite images. And here in Trinidad and Tobago, you can readily acquire satellite images, I beg your pardon, aerial photos from the Lands and Surveys Department, which is available for public purchase. So choosing to use aerial photos may depend on the scale of the project and the cost, as I mentioned. So if you're doing a small scale project and you don't have money to spend, you may want to choose aerial photos. Another question you would want to look at in order to decide whether you do aerial photos or satellite imagery: what is the size of the analysis area? What's the geographic scope? So in small areas, aerial photos are less expensive, but as you start to increase your geographic area, it increases the cost. Now, if you want to use aerial photos as your geographic area increases, you can basically stitch those aerial photos together to create a mosaic or a much larger aerial photo, but this is very time consuming work to get it done accurately. Satellite images, on the other hand, can cover much larger areas. As I mentioned before, they can capture much larger geographic areas because they are capturing their data at a higher orbit than the aerial photos would have captured. Alright, and as well, you will find that the result of those satellite images would have less terrain distortion than the aerial photos. Satellite imagery is less expensive for larger areas because you will have lower resolution for larger areas. When you get into higher resolution, now you will have more expense. Okay. The other issue you'd want to consider as well is what level of detail do you need? Do you need a broad spectral range where you can see both visible and non-visible energy signatures? That is also something you'd want to consider. If you need that level of detail of data, well, then you would want to go with satellite imagery. And additionally, the inherent digital format of the satellite image is an advantage because it automatically comes in a digital form, whereas when you collect aerial photos, it will first have to be converted from that paper format that they will give you into an image, and then you'll have to do your georeferencing, etc. Right, so continuing. Satellite images may also require specialized software and training for it to really be effectively utilized. So, because remember, some features may not be visible with the naked eye, so the data would have to be manipulated using special software by persons who have been properly trained to utilize it. These persons are persons we refer to as remote sensing specialists. Alright, now these remote sensing specialists would usually also have to be trained in a specialized area. For example, it may actually be a forester with remote sensing training, or it may be let's say, for example, a soil scientist with remote sensing training. All right, so for the rest of us, we would really just utilize the final map product on our map for viewing, because all the hard work would have been done before. So in conclusion, we just wrap up with a reminder of some of our other sources of data input into our GIS. We just looked at remote sensing in some amount of detail. So if you recall, at the start of the semester, we identified hard copy maps as a source of data, where those hard copy maps would have to be converted into a digital format through automation or scanning. Additionally, other forms of documentation, such as written documents or printed documents, can also be put into the GIS, where, for example, you can link those documents to certain features. Getting back to the various types of maps, if you recall, you should recall that we talked about feature maps, representing features as points, lines, and polygons. We talked about choropleth maps. For example, a population density map would be a choropleth map. We have dot density maps, which can also show population density, but it uses points to represent specific values. So this type of paper map here represents clusters very well. And then we also have our isopleth map, or a contour map, as most of us would be familiar with those contour maps. But those isopleth maps can also represent rainfall, elevation, temperature, etc. Then we also have global positioning system. That's our GPS. This is another technology that can be used for data collection that will be used in GIS. So global positioning systems, it's a radio navigation system that uses satellites to provide location information as well as navigation information. Okay, most of us are familiar with this technology, even at a most basic level, because our phones actually have GPS capabilities. These are the main components of our GPS. So you have the user component, for example, your phone. You have a control station here on the earth at some particular location, and then you have the satellite component here. So what actually happens is you have a triangulation process that takes place amongst the three components in order to establish your location at this point. Now, typically when we have this process going on, they would use more than one satellite, of course, and that is in order to establish precision. If you recall, precision is a repeated capture of measurements in order to establish accuracy. GIS data can also be captured using surveying methods. Now, this surveying we're talking about here is engineering surveying that captures information and measurements on about features on the Earth's surface, right? What does it measure? It measures features and relationships in terms of points, location, distances, lines between features, and the physical features themselves. So the main thing to remember is that it determines horizontal distances, elevation differences, directions, and angles. So if you look at all of these parameters, you know that this is information that can actually help you to draw features on a map, right? Here, this is an example of the equipment that we call a theodolite. This captures that type of information. So at this point, I'd like to thank you for joining me for today's lesson. Please refer to eClassroom for further instructions. Thank you.